No problem.
Okay. Well, I want to thank everyone so much for joining another Balerion Space Ventures podcast. It's May 11th, and today we're joined by Scott Graybeal, the CEO of Caelux, company that revolutionizing solar with their patented perovskite technology. Uh, Scott, thank you so much for being here. Maybe to get things kicked off, you can walk us through a high level of what Caelux is doing and what makes their solar so unique.
Well, thank you for having me, Aidan, and appreciate the invitation. So, Caelux is producing on 1 by 2 meter sheets of glass what could be effectively described as power producing glass or power generating glass. And in our terrestrial PV business, we work with large module manufacturers that replace the standard clear glass that's part of the architecture of any traditional crystalline silicon module with our power producing glass. And then effectively, you're creating two power layers, double power layer, basically. So the perovskite is better at absorbing higher energy light than the silicon is. The silicon's good at absorbing lower energy light. And together, you can actually boost the output of a module by about 30%. And so, as we see the crystalline silicon technology and terrestrial plateauing, this becomes the added boost that's needed to take us above 30% efficiencies in a reasonably short period of time. We've been the first to commercialize this technology in the US and are shipping to customers today.
Fantastic. Now, this solar that you have, it's much more efficient, and solar, it's kind of been around for a little bit, and it feels like it may have plateaued. Tell us about just the journey of the solar industry in general, and if there was a point where maybe you saw a pause, and what the revival right now is looking like for the future of this industry.
Yeah, I don't think we've seen a pause. I think the only pause that we really saw was during peak COVID. Every forecast that tried to look at a plateau was wrong. The one thing that does, I think, hold back the adoption of solar are more regulatory topics, interconnection, permit queues being quite long. That's the only really challenge. When I started in the industry 18 years ago, we were still talking about hundreds of megawatts of deployment. And now we deploy roughly 2 gigawatts a day. That's 2 gigawatts, 2 billion watts of PV a day. So it has not really plateaued. In fact, it's continuing to grow at a double-digit CAGR. I think that there has been some rhetorical misinterpretation, particularly in the US. That is not the case. We're seeing solar companies that are stronger than they have been before. We've seen a tremendous amount of investment in module manufacturing to the extent that the US could be fundamentally self-sustaining in making its own modules. Now there's other inputs that it would not be self-sustaining in, and I think there's more investment needed. But perovskites are an incredibly important leg of the supply chain going forward and really will be the harbinger of the future here in terms of what the where the industry is going. And so, today we're producing some of the most advanced photovoltaics in the world in the US.
Interesting. So I want to get a background on you with your journey of how you ended up here, because you didn't found this company, but you are CEO. So what led you to this point, and where did you see the opportunity to where you said, this makes sense, it clicked, and you went and became the CEO?
Yeah, it's been an interesting journey for sure. I grew up in Los Angeles, and when I was a kid, I remember having smog days, where you couldn't go outside. The air quality was so poor. And that always stuck with me. And my first journey into the energy business really started when I was a nuclear submarine officer. So I was trained to learn how to generate electrons for usable applications. And so that's where I first really embraced the concept of energy and that being a potential career option. And I took a detour to semiconductors after leaving active duty, but which gave me a foundation in the kinds of technologies that are needed to make efficient solar. In about 2008, I made that transition to PV. and really haven't looked back. I had one break in my career, but I was an angel investor still, even when I was outside of the solar industry as a professional occupation, but still participated in it because this is an opportunity for us to really manufacture ourselves out of any sort of future energy crisis. And when you look at the combination of high energy density solar like we produce with long duration energy storage, you can get to 7 by 24 dispatchable solar. That's the vision. And we're not far away from being able to do that cost effectively. So, for me coming to the company, I had a background in material science and chemistry, and that was very helpful. Though I work with some brilliant scientists and some of the top scientists in the world in this field, it's nice to be able to understand the fundamentals of how your product works. And so that was helpful. But I came from a pretty deep operations and commercial background that lent itself from taking a company that was 8 to 10 people when I started to now 80 people, and we're operating in 3 different countries.
Wow. And maybe for non-material scientists listening to this, what's the easiest way you can explain what perovskites can do that other solar panels, silicon solar panels, just simply can't?
I don't know if it's different that what they can do that other solar panels and other technologies can't, but it can do so cost effectively and it's demonstrated a tremendous amount of radiation resistance. So a perovskite is nothing but a mixture of metals and nonmetals that, when the process under certain conditions, can produce very cheap, very powerful solar cells and very lightweight. And so the thickness of the layer that we deposit on glass, for example, is less than a micron. And so it adds no weight to whatever your substrate that you're using, whether it is 3.2 millimeter glass we use for terrestrial applications, 2 millimeter tempered glass, 2.7 millimeter willow glass, doesn't matter, or even a polymer substrate. So the combination of lightweight, high energy density, and radiation resistance really lends itself to other applications beyond terrestrial. And we do have active engagements around what can be done in space.
Fascinating. And for in space, are we talking things have changed where now we want lunar bases and data centers in space? Is that what has changed that really brought this into that industry? Or is this technology really that brand new and it hasn't really existed at commercial viability for or commercial sales for both terrestrial and solar? Is this anywhere else you can find it in solar fields?
No, it's fairly new. I mean, these properties of these materials weren't discovered until 2009.
Oh,
And
wow.
so when you look at how long we've been working with silicon, it's almost 100 years and really in earnest since the 1950s. So that technology is 70 years of characterization, right? We didn't really see the first solar business start until the 1970s, or this first solar industry more specifically. And so there was at least 50, or excuse me, at that time, 25 years of experience with the material before you started seeing it being used in photovoltaic applications at any reasonable scale. And so we're very much in the early part of this. And this is why I think it makes such a compelling investment opportunity for folks, is that you're not behind the wave, you're in front of it. In fact, it's beginning to already crest. And we're going to see perovskites really become a meaningful part of the solar value chain very shortly. So, we ourselves have gigawatt expansion plans that we're working with financiers on. We have, as I mentioned, active engagements in aerospace and defense applications. And I think it's the realization that this technology and in the world of AI, which also features quite strongly in our research and development pipeline, um, is helping to accelerate discovery and using those tools to help us with experimentation and maybe areas and vectors we wouldn't have otherwise thought about. So I think we'll see an acceleration of the deployment of this technology, unlike we saw, let's say, in legacy PV, which is oftentimes quite reluctant to embrace new things unless it's forced to. And so this is going to really have a dramatic change, I think, on the overall market. And I think our strategy has really been to work and stand on the shoulders of these giants that have already blazed the trail. And then let's get perovskites out there into the market where companies and individuals can get used to the idea. And hopefully we come up with a better name than perovskite because nobody likes saying it. But I think that the applications are manifold. Our CTO authored a white paper has since been signed off by most perovskite companies about the future applications, and it doesn't stop with just PV. There's radiation detectors and LEDs and a lot of other things. So we really view this as being at the tip of the next wave of optoelectronics innovation.
And when you're comparing it against traditional solar, what's the score look like? Like, how much lighter are these panels? How much cheaper are they? How much more power do they really generate? So we can get an idea in our head.
Yeah, I mean, it's not unusual to see perovskite solar cells that will generate on their own today in the 20s at smaller sizes and industrial sizes, 17, 18%. We ourselves at mass production are between 16 and 17% as we're shipping this for our double power layer or tandem module customers today, which is resulting in them being able to deploy modules that are 26, 27, 28% efficiency. And so you can see how the crystalline silicon and perovskite tandem world has evolved. But if you look at perovskites only, there is plenty of headroom for innovation, and perovskite only tandems can have, and that's when I say tandem, that means putting one cell on top of another. And the electrical connection I won't get into and all that good stuff, but that's what we refer to as a tandem. And you can see those reaching in the high 30s quite easily. I think the world record for 3.5 devices is about 38%. I think perovskites are going to be able to hit that in production at a scale that's meaningful. And so when we look at the cost advantages of perovskites, this is a fundamental shift in what I call PV 3.0. 1.0 was the 70s, 2.0 was the early 2000s, early to mid 2000s, where crystalline silicon really took off, and 3.0 is the age of perovskites. And these can be manufactured much more cheaply, primarily because they use about 1/20th of the energy necessary to produce a crystalline silicon cell. So let's say you're a country that subsidizes electricity cost dramatically, like China. You have an advantage, right? In the marketplace, you can strip mine coal in northern China and then provide that as fuel for your polysilicon plant. Whereas for perovskites, we're talking about inorganic and organic materials that are readily available that we can mix together in certain process conditions to produce these cells. So there's no advantage for if you were a super low cost energy producer to for your industrial capacity for perovskites. And likewise, the manufacturing of these devices is quite automatic. And so when I think about lunar bases in the future, this one I like it quite a bit because it's even applicable to things like asteroid mining and whatnot. But if you could imagine in situ printing out more solar in the event that your array gets wiped out because of micrometeorites or dust or whatever, you have the ability to now go ahead and print out more solar and deploy that effectively at whatever it's your station or your base that you may have. And so I love that idea, right? So how can you make these installations self-sufficient from an energy production standpoint? Well, it's not just about sending them panels up on a rocket. That's expensive. But how can you do that in situ with some chemicals that you have that are quite easy to produce and be able to synthesize this in situ? That's a little further down the road, but I think since this is a space-focused podcast, I wanted to just share that. Being able to in mid-flight, being able to repair an array, for example, instead of having this be a catastrophe, have the ability to go print out more solar using hopefully in the future much smaller, much lighter process than we have today. But it's possible. Everything that we're doing today lends itself to miniaturization and lends itself to a degree of automation that effectively you hit start and then you're done. And that's what we envision for our production. And so, we can run multi-gigawatt facilities with literally a handful of people per shift. And that's because it's an inline process and something that I think that can be miniaturized and simplified in the future for sure.
Yeah, and thinking about it, could you give us like a simple explanation of what's different between solar in space versus solar on Earth? What needs to be changed, and how can it be more effective, and what are the trade-offs or benefits for each?
I wish I was more of an expert on space. That's our founder, John, who worked extensively in 3.5 materials and was a world record holder in that technology node. And he worked extensively in space. But from my knowledge, it's really going to depend on altitude. If you're talking about low Earth orbit, you have to worry about chemistry. So things like atomic oxygen and whatnot. But if you're further up, then that becomes less of an issue, and you're really talking about radiation hardening. And perovskites have demonstrated incredible ability to take damage and keep going. These structures, they're photovoltaic, or they express photovoltaic properties not because they have perfect crystal structures, it's because they're extremely imperfect. And that's a mechanism that's been recently discovered by a European lab. For a long time, we didn't know how these things actually were photoactive, and now we've got a reasonable idea. And it's part of that in situ chaos, if you will, that becomes helpful. But these devices heal themselves, and we got to see this practically. So we deployed on the Alba mission with Caltech, and that particular spacecraft had experienced a solar storm. So it had a huge proton flux that hit the spacecraft. Most of the devices died, but our perovskite device did quite well and managed to recover. And so we're excited to get more data about that, and that's forthcoming. But we've demonstrated the same thing in laboratory experiments where we exposed perovskites to very high proton fluxes and have done quite well. So I think that's going to be the superiority of perovskites over silicon in the long term here, is really that resistance, that intrinsic hardening that these materials have for for that application. You touched on cost earlier. It's hard for me to talk about that insofar as I know terrestrial is quite cheap, but space has very, very exacting standards. So we're going to be working on that, but safe to say it'll be less than silicon. It'll be much less than 3.5, significantly, such that this, with lightweight and low cost, it becomes almost a no-brainer for space companies to embrace the technology.
Yeah, and just being lighter, being able to send more up. How is this brought up into space? Are they on these fixed panels? Can they be rolled up? How does the array really get put out there when these panels
Both.
hit space? Okay.
Yeah, today it's mostly done on super thin glass. But you can, we've already done extensive experiments on flexible materials. We know it can be done. Our line today is not configured for that, but for us to do it, it's fairly straightforward. We are working with a leading roll-to-roll producer today that has other applications, but that they're bringing their process knowledge to the party. We're bringing our deep perovskite knowledge to the party. And so we'll get this sorted out. We're able to do it at scale. And I think in the short term, it's quite simple for us to make long devices that are on flexible substrates. It's not the most efficient manufacturing process, but it can be done today. So, I think that the best solution is to have something that can be collapsed, almost like an accordion, or rolled out, right, on a spindle. And that's how we think about it. And I think that would be really the objective. But, baby steps. We can go out with, let's say, more rigid platforms today, and in the future, with the right interest from the market, we can do a lot of things.
And can you make a case for solar in space when people are looking at alternative solutions such as nuclear, small modular reactors, radioisotope batteries as being sort of a new entrant to providing energy, both lunar in space?
Mhm.
Yeah.
Um, yeah, I think it's got to be a part of the mix, right? I mean, my background was in SMRs, and so there's pluses and minuses with any technology you have. I think the waste disposal consideration has always been one of the major challenges associated with nuclear. And until that's really licked and can be commercialized at scale, I think it's going to be problematic. There's an element of safety that we don't really have in our space, no pun intended. But I think it has to be part of the mix of how we think about uh, colonization in space, how we think about establishing bases in space. I think you need to have redundancy. I mean, that's the one thing that we had in submarines was redundancy. Aircraft has redundancies, and for sure, a lunar base or permanent installation of humans in space will need to have redundancy. And so we're an extremely important part of that. And given the fact that you may be able to point something at the sun all the time, means that you've got really cheap energy that can support your flight or whatever you're trying to achieve.
Got it. And as you start manufacturing and scaling this up, what does this look like from supply chain control aspects? Are Is China still dominating this space? Is manufacturing still happening over there, or have we started manufacturing in the United States? I guess what can be expected over the next 5 years in terms of who's making these, who's producing them, who has the materials?
Yeah, I think perovskites reset this entire conversation tremendously. The
Okay.
challenge that the US has had in solar is the fact that you have to invest in very large polysilicon production facilities, I think, to be successful with a completely integrated, vertically integrated value chain like China has done. There's no secret to what China did. It was basically Wright's law that we figured out in the aircraft industry in the 1930s, and they just turned it around and showed us our math again. They invested a lot of money in it, right? They invested a lot in polysilicon production in Outer Mongolia. And likewise, we're able to really dominate. And they put a lot of money as a job creation project, really, into PV in China. And the West had an opportunity to do it. That's a whole other story we can go into later, but the West had turned that down. And then that just gave an opportunity for China to point investment dollars at it. And consequently, they dominated in PV 2.0. Where that gets reset is that some of those traditional competitive factors that China had, specifically cheap electricity, low labor costs, low regulation, um, and a lot of capital, let's be honest. They were able to harness that to go and create this leadership position. Since we've had a regulatory shift over the last decade or so that's been more pro US manufacturing, we have since seen that there's been a resurgence of US solar manufacturing. We had announced a 3 gigawatt manufacturing supply agreement with a company based in the US in Puerto Rico, a company called Solex. And so that was the first and largest commercial deal of its kind for perovskites. That's made in America. So that is something that's happening here. The most advanced photovoltaics in the world are being produced in Puerto Rico. And so that's an exciting time. And I think that given that these technologies really reset that paradigm about manpower, about electricity costs, it gives the US an opportunity with proper focus to really take that leadership position back. We're the second largest solar market in the world.
Got it. And maybe you can tell the story a little more on the US, the technology we had, and the moment it we lost our path and China seized the opportunity. What were some of the key defining moments? And if you were able to go back, what were some things you might put into policy or rules you'd want to make so that we wouldn't have to be playing catch up in the current
Yeah,
state we're in?
I was a free trade guy for most of my career. And I think that the realization that we all had is that it wasn't an even playing field. If everybody's playing by the rules, then, may the best company win. But there was an artificial inflation, I think, of the capabilities that were provided to the Chinese producers. And so I think we were slow to come up with the proper, let's say, proper and legal restrictions that undermined the US and European solar industry, quite frankly. So I think that was hugely problematic. We didn't recognize this as being a problem. And now you have not just the United States, but India, Saudi Arabia, and other players in this market have said, okay, if we have this great resource of the sun in a lot of our geography, why aren't we creating jobs to tap into it? And I think that's the right thing to do. I think it gives, and I think putting these companies on, let's say, resetting that paradigm altogether earlier, I think would have been a better story for U.S. PV production. Though I think it's important, though, that when we talk about these tariffs, that there's still competition. That's an important feature, right? Because I do think that companies that are too protected have a tendency not to innovate. So you have to strike a balance. So competition is good, but it's got to be fair competition. And if it's completely a taxpayer driven or country treasury driven conversation, well, that's not really fair. That's not market, right? That's not a free market. So I think it's a realization that, we needed to have some fairness brought into the system. I think if we did that earlier, we'd probably have a more robust PV industry today. But to see companies coming up now, it's an exciting time. Is that now you see that the US is saying, okay, enough's enough. Now we're going to go create good paying American jobs doing this. And there's an opportunity to do that. And I think to really carve out a position that recognizes both quality, domestic production, and provides for, the US to be able to further monetize this amazing asset we have. And that amazing asset we have is sunlight in most of the country. So
Yeah. And is there anywhere in the solar industry where the US is ahead, whether it's advanced materials or, something like space applications, software, power applications that work for electronics in a more modular way, uh, or maybe something else?
yeah, I think that look, I think the US is hasn't lost at all in this game. I think it's now could it have? Yes. I think if given more time and if we just allowed low cost Chinese goods to come in, I think the US would have lost. But you see some very strong companies out there, right, that are either emerging or they've been around for a while. And in the electronic space, you can look at Rooftop. You have companies like Enphase, US born and bred company that dominates the microinverter space. You've got companies like Nextpower dominates the tracker space and AI deployment in power projects. And I think in solar now you're going to see this renaissance on the manufacturing side, and you're going to see more cell manufacturing that's done here in the U.S., which is great. As we think about, these double power layer modules that we have or tandem modules that we have, having that supply chain here. So I think it's a turning point. It's absolutely a turning point in this industry. And I think and we see this again globally. We see it play out in India. We're seeing it play out in Saudi Arabia. And maybe one day we'll see Europe really embrace it. We're starting to see the beginnings of that conversation really gaining some steam. So, I think this is it's the perfect time for investors in particular to look at this landscape and say, you know what, things are changing, and they're changing in such a way that gives more diversity to the market. There's more opportunities for investment, and this is a technology that is sorely needed. You look at what's happening in the AI space today in hyperscalers. Heck, you had Google acquired Intersect Power. What's that tell you? They bought their own project developer to build more solar for their data centers. We're going to see more captive power applications. And in the future, as data centers become more efficient, then that captive power may be spun out and wheeled out to other applications, i.e., the grid. So this is a very dynamic time for this industry. And to be frank with you, when I was not eager to jump back in professionally, leading a solar company back in 2020, because I had that experience of taking most of these jobs. We had manufacturing in here in the US, we had it in Canada, Mexico, Malaysia, and to watch that all dry up because China became so dominant was a painful thing, and not just for me, but for everybody else in the industry that was outside of China. You just couldn't compete because of this level of subsidization that really allowed the scale to drive the cost so low that it became very difficult for others. Now, I think where the US is going to continue to have an advantage is on the innovation frontier. And I would say that, if you would have asked me 6 months ago if I thought that the Chinese were ahead of us in perovskites, I would have said yes. And today I will tell you the answer is no. I think that the US is caught up, and Caelux in particular is caught up. So we're pretty excited about that. But the way that we do things is different than how they're done in China because we didn't have, let's say, more of a groupthink mindset around certain aspects of the process technology and the cost structure. So we attack this problem as our competitors would. What is the cost going to be? What does it need to be? And design your process and design your product to meet that requirement, not just for today, but what's it going to look like in 5 years? What's it going to look like in 10 years? And so the supply chain The challenge we have in the supply chain in general in the US is the lack of scale. So I think investments are made to scale these technologies, these base materials technologies that we need, then I think that makes life a lot easier. As it sits today, we still do import some materials from China. That is becoming a diminishing part of our mix, and we have a bill of materials today that we could exclusively source from the US. We have a bill of materials that we can source from US allies and the US. So it forces us to be more flexible, and it drives a conversation about scale investment for suppliers that doesn't just stop with our supplier relationship, but also working with the investors of our suppliers and saying, look, if you do this, then this is what we expect, and this is what we think we could see in the market.
Yeah. And as you're talking about where we're advancing with just our use cases, advanced materials, and just maybe just creativity, is there a future where, we start seeing solar used much more frequently because it's cheaper and produced at home and maybe used in ways that aren't today? For instance, Elon had the solar company with the solar cells that were roof shingles, and I've heard of solar companies putting their panels in, office buildings, windows, and you have a window that's now tinted, but it's actually collecting power.
Yeah.
Is something like this a future we might be seeing in a very short time?
I would say yes. And I won't get into the pros and cons of solar shingles per se, but just I'll leave you with this. Heat is a tough thing to deal with. And so you got to be mindful of that. But here's an application that is gaining momentum, and it's already taken off in Europe and that we're going to see in the US. And that's the concept of balcony solar or plug-in solar. Just today, I got an email from one of our VPs that said, hey, Colorado just passed a law allowing balcony solar. And what this means is that people that are in apartment buildings can go and buy a panel, plug it into their wall, and they're going to be able to get a part of their electricity load covered by this panel. And we think it'll be even more powerful if that is a double power layer tandem module. That will be like a much more efficient product than if they just got, let's say, the more traditional consumer grade type panel. And so you can just imagine the balconies in the short term are going to be covered with solar panels in many places. And so that's an easy one. The building integrated photovoltaics, people love it. Architects love it. The people that don't love it are the guys who have to write the check to build the building. I'm being honest here.
Yeah.
Now, how can you simplify that? Well, there's lots of ways to simplify it. And I think that one of the simplification, and here's the issue. It's not anything to do with the core technology. It has to do a lot with the wiring that's needed. And so you have a pretty substantial balance of systems impact. Every window then needs to be electrically connected. And you can imagine that's really where it becomes more challenging. And so we will see, perovskites have a building integrated photovoltaics application today. Can we do it? Yes. It's a small part of the market, and it's a very unpredictable part of the market. So you spend a lot of time out there talking with architects, getting your product designed in, only to have, the building owner say, hey, I'm not writing that check, sorry, unless they really, really want to. So it's there, unfortunately, and I'm sure some people on the call will probably groan, but it's a bit of a niche. Rooftop, though, continues to be strong, and it's an application that you don't need to have brand new technology sorted out to go do. But in the future, we could be looking at perovskite paints. We could be looking at perovskite window tint and things like that. That's doable, but keep in mind that you got to get the electrons out of the device at some point, and that's where oftentimes it becomes more challenging.
Yeah, it's interesting. And I'm thinking all these creative ways we could use it, uh, and then taking that to space. And I'm curious where you see the first big commercial crossover, whether it's, mega constellations or high-powered satellites, lunar infrastructure, or maybe something else a little more niche, like in space manufacturing or defense assets.
I think all of the above, frankly, and I think the thing that's exciting about constellations and small sats, is the fact that weight is at a premium, and that's an important consideration in cost. You want to keep the cost down. Perovskites lend themselves to that quite readily today. That's really something that can be done. In fact, we're working with a couple of satellite companies today. And that I think is going to be straightforward. Now, one is in a more advanced application, one is in a more, let's say, consumer type application. Consumer being, hey, small satellites, more that telemetry type thing. So anyway, but nonetheless, I think that the technology is going to be available to be integrated off the shelf by designers that are curious to do so. And so we haven't turned a phone call down yet from anybody who's come from a satellite company saying, "Hey, I'm thinking about perovskites." Well, great. We have experts for you to talk to. We've been putting, as a team, we've been putting stuff in space for 30 years. So, there's people on the staff that know this market inside and out, and that can readily help you with that particular application. So, I think it's probably going to become a default conversation. And if somebody wants a really high power density application and it does, they're less worried about radiation hardening, then okay, then we can have a conversation about a tandem device. If it's something that, hey, it's going to be a high rad environment, you want something light and flexible, okay, then maybe a perovskite single junction device. In the future, we'll be talking about perovskite tandem devices where we have a low band gap perovskite and a high band gap perovskite. That's the future. But there's lots to explore, and this technology will continue to evolve and iterate. And our strategy has really been to be the first out of the chute and to make sure that we could scale and support the broad requirements we think is going to be the next wave of PV innovation.
Yeah, and I'm thinking just in space applications or even terrestrial applications, if there's other technologies that are coming out that are quite interesting, and solar plays a big role. Things like power beaming from space, where energy is collected and shot
Right.
back down to Earth. And then there's other things like energy directed weapons, where high-powered lasers are shot at another satellite and to scramble their circuits or fry their solar panels. Where's perovskites fit into this new wave of directed power?
Well, clearly a part of that, and it's hard to say because, when you look at how these devices are engineered, they're probably tapping into multiple redundant power systems. I think we fit into that equation. I think in terms of, is there a direct application? Well, we generate energy. And if that energy is directed in one direction or another, whether it's back to the ground for power consumption or to an adversary satellite, we're part of that mix. And it depends on the engineers how much they're going to rely on solar versus, let's say, other power systems such as nuclear to support that application. But if it's going to be part of that solar mix, then it definitely, why not get the highest efficiency, lightest weight technology in orbit that you can?
What do you think the most panels you'd be able to send up on a single Starship would be? Because I'm imagining these in-space data centers, and they're going to be huge, and some of them are going to have giant solar arrays. And I'm wondering how long that takes to build. With these perovskites being so much lighter and being able to be rolled up and compacted, would you be able to get something that's the size of a football field up in space within a year? I guess it depends on launch cadence, but
Yeah, I mean, I think a roll would probably be the simplest way to do so, right? And having some sort of mechanism that can go and run it out to the length that you need it and stabilize the array and point it in the right direction. I think there's a lot of savings on weight to be had there, particularly if you don't have to have robust framing. And if this is a system that can self-repair, then that's great. I think you get a significant, I haven't done the calculations on that, but you can imagine a roll is probably covers several football fields and in length. So that's not as far off as you may think it is. I think if we
uh,
were to get the right partners on that, and if it made sense for our shareholders, and we could certainly, drive in that direction.
yeah. And say if launch costs just dropped by an order of magnitude tomorrow, like what kind of crazy solar in space ideas would be feasible and maybe you would personally fund?
Me personally, fund.
Something that you think would be a great opportunity and maybe it's not right now because of the price of launch, but if it were to come down, it would be much more feasible and something to really look into as a great opportunity.
I got to be honest, the whole idea of beaming power down from space, it sounds good. I think the devil's in the details, as most things are. We have plenty. You don't need a ton of real estate, let's say, to go to satisfy global energy requirements with terrestrial PV. You could take the tip of Nevada and basically cover it with PV, and that's enough for the United States. Okay, so we're not talking about huge amounts of land. And when you're looking at high density solar, that shrinks even more. This conversation around land use comes in areas where there's a debate about agriculture versus power generation, right? So, I mean, I don't think that terrestrial is necessarily dead. I don't quite have the math behind what is the efficiency in converting this to microwave and then taking that and then turning it into usable electricity terrestrially. So if that's all sorted out, let's say that's an infinitely efficient, or has the efficiency that's necessary by transmitting from space down to Earth. Let's just say that problem's solved. Then you have a lot better irradiance in space. There's no doubt, right? I mean, much better conditions because we have no atmospheric filtering, right? Which always becomes a challenge. That's why we talk about AM 1.5 G here, which is, hey, we've got 1.5 atmospheres that we're looking through, and this is going to cause less energy to be converted. So you're able to really tap into, at least 1.3, was it 1.36x the irradiance in space versus what you could see terrestrially. That's great. That's significant. That's a lot more power. So if that piece could be solved, that would be a fantastic way to support our energy requirements.
Yeah, and I'm thinking about lunar bases and just lunar infrastructure
Yeah,
in the future. The first thing they're going to need is power, absolutely.
absolutely.
But the moon can be tricky. By one side, there's no atmosphere, there's no clouds or weather. It sees the sun quite a bit, but it also has 14-day nights and rapid temperature shifts. So, what's the future of lunar bases look like? They're powered by solar and having to deal with these harsh lunar nights, temperature changes, things like that.
Well, you're probably looking at a handful of things, right? And one, you could be looking at SMR, you could be looking at solar plus a significant amount of storage. You could see, a lot of those technologies. I think you're going to need to have redundancy no matter what you do. And so this becomes a part of that equation. And I think if you can tap into both, why not? In the event that let's say you even had two SMRs up in orbit or up on the station, you would still probably want to have a redundant power supply. And when it's not needed, why not extend the life of that reactor and shut it down and be able to just support your base with solar and your long duration storage? So I think it's a harsh environment to be in. And give you an example. I mean, I was on a nuclear submarine. We had redundancy. We had two types of redundancy. We had a diesel generator and we had a lead acid battery. And
It must
so
be a big battery.
it was a big battery. Yeah, I crawled on top of it a lot when I was an ensign. But these are substantial. And so there were even, we had to think all the time about redundancy of systems. And those are three different architectures. You have a nuclear reactor, you have a diesel generator, and you had a battery. We had three different types of power systems. We had redundancy in how we produced water. One was based on steam, one was based on electricity. So there's all, and I look at that as really kind of like an insight into how we have to think about surviving in space, which in some ways is a little easier in a sense. You don't have to deal with the high pressure environment that we did, literally high pressure, versus, okay, you really have to deal with keeping one atmosphere inside of the bubble. That's a little bit easier in a sense, but you'll still have to have redundancy of power systems. Now, you can't run a DG set on the moon. That's not going to work for you. Can you run a battery? Absolutely, depending on the cut type. And so you also want to have redundancy in terms of generation. And that generation can come from nuclear as well as it can come from solar. Unfortunately, no wind. So there's no wind.
Yeah. One of the ideas I had is we were just talking about power beaming, and I was thinking LLO, which is low lunar orbits, having these, power beaming stations that could power up, the panels during those 14-day nights. I know that might be a little far out there, But with all the problems that exist, there seems like there's some kind of workaround. Of course, redundancy is a must, but
Yeah.
maybe you just get really big, solar fields on the moon with big batteries and, they can stay charged for those 14 days, things like that. But then I think about going further out and going to Mars. Would it be easier there without having those long nights, even though it is further away from the sun?
Mm. Well, I think in Mars you have different set of challenges. You do have a tendency to have dust storms, and some of those can be quite long. Now, I think The Martian was wrong in showing just how powerful these dust storms are because there's like very little atmosphere, so you don't get that kind of force. But you still have to worry about damage to an array, soiling. And so those are the types of things you have to be sensitive to. And this is where I like the idea of being able to produce solar in situ, whether it's a mining operation or if it's on Mars, being able to go and print out additional solar in the event that is damaged by whatever atmospheric event that may hit the Martian surface. Um, but I don't think you're going to get away from having to have solar, and I think having the ability to f- rapidly repair and restore systems is going to become at a premium. So why not go up there with the materials that are needed, and then you can go and deploy it as needed, as you need to go and repair things, as opposed to setting up a bunch of rigid solar panels that take up valuable cargo space and weight. Just send the raw materials up, send a bottle of materials that you need and the printer that you need, and have a couple of those laying around and the substrate you need that probably has more than one application. And then go off and print out what you need to support the base that you've established.
Yeah, and I'm thinking about it, and solar is tough, and it can do harsh environments. I think about Opportunity, the rover that was on Mars, in the early 2000s. It was supposed to be there like 90 days. It lasted nearly 15 years,
Yeah,
and eventually windstorms,
yeah,
and a couple other things ended its
sure.
life. But this is technology we had in the early 2000s,
Yeah.
and as things have gotten better, I have a lot more hope for solar in deep space and on Mars. Um, has the technology really gotten better, or do we just have, better redundancies and solutions to fight these issues and challenges we might face?
Well, I think that like if you look at crystalline silicon technologies and I don't know what devices they had on the rover, if they were using 3.5s or what. That's something I hadn't thought about. Um, but I think that we do have the opportunity to make things even more dense and even more energy rich so that you could charge batteries more efficiently, more effectively. I think that's a fundamental difference that we have today versus what we had. I mean, the panels are going to be 50% more efficient than, what we have today, right? And so that's something for us to really be interested in and look at that as sort of like a new design input as we're thinking about these deployments. Um, and kind of just thought of something that I should have mentioned before. We're talking about the moon base. Now, part of the reason why we want to go to the moon is we want to be able to produce fuel, right? So taking lunar water, converting it into, or lunar ice, converting it into hydrogen to go and support fuel for this ongoing, mission to Mars. Well, that's also in and of itself a storage medium. That if you think about it, if you're doing that anyway as part of your excavation to go create rocket fuel for your next mission, and splitting oxygen and hydrogen, that in and of itself becomes a storage medium. That I just wanted to circle back to that point because it was something I neglected to mention. We're talking about long duration storage and dealing with those long lunar nights. That could be part of that equation.
Mhm.
Electrolysis is cool. But when you start looking at getting out to Mars, that becomes interesting. I think about more mining than I do about really Mars itself, because I look at the economic opportunities that are available in mining, asteroid mining in particular. And you have a lot of metals that are floating around there that could provide the right kind of economic impetus to make something like that work. And I think about in a mining operation, if you're circling around and you're doing what you need to do, then having, again, on your spacecraft, redundant power systems and the ability to self-repair would be really important.
Yeah. And with the mining in space, Do you see the opportunity in like the platinum group metals that are on asteroids, or maybe things like helium-3 on the moon?
Yeah, more of the platinum group materials, just because they have such a. I mean, it will clearly tank if they can be done inexpensively enough. I mean, they would really, it would be disruptive to commodity markets here on Earth. But it's not the first time we've dealt with that. I mean, the Spanish had the same issue with gold when they went to the New World, right? So
Yeah,
actually debased or devalued gold significantly. I think that our appetite for platinum group metals is going to continue, and having a rich source of those metals, they do things that otherwise are quite difficult to do, right? I mean, they make amazing catalysts, and they're important for our microelectronics. We shouldn't be restricted on our ability to innovate based upon the access to raw materials, and that in and of itself creates an opportunity for plentiful raw materials. Just the question is, if the price drops so low, do the economics still pencil out? And that's kind of a funny equation to solve for. So there's going to need to be a different impetus to doing so. And so, being able to harness that, as long as these materials are part of our electronics machinery we built, then we're going to need to find plentiful sources of them. And there's clearly plentiful sources there.
yeah. I'm thinking with the moon and Mars bases, and just the first thing we're needing is power. Like that's obvious. What do you think the second and third thing are?
Air and food.
Air and food. We're
I
not
mean,
going
if
to
you're
start
talking
with
about people
robots.
being there, right? I mean, those are the
Yeah,
things,
yeah,
right? I mean, just kind of you come back to your hierarchy of needs, right? So, course power, well, that kind of deals with your warmth issue and just the systems you need to stay alive. And so, air is an important consideration. So, do you have scrubber technology that is small enough, compact enough? How efficient is it? Having had to make my own air, it's something that we considered a lot, right? In a submarine environment, you didn't always
yeah,
have the opportunity to, snorkel. So being able to produce oxygen reliably and safely is a real issue. And so, as long as you can keep the air inside the bubble and there's no holes in the bubble, that's a good thing. And then you have water, of course. So air, food, water, those all kind of come together as really, really important. Water is a tough one, but the moon provides some opportunity for water. Mars, I guess at the caps, but I think that's CO2 ice, if I'm not mistaken. It's been a minute. That's probably a
yeah,
little bit more difficult. Um, I think a lot of folks are enamored with Mars. I think it's more of a question that you just pop your flag on it and call it good, and then go out to the asteroid belt and realize some real economic opportunities. Does that become your waypoint? Probably. But does it go beyond being a glorified bus stop? I don't know. Whereas I think the moon really offers some really near-term advantages that should be harvested. I mean, to me, that's really kind of our launching point into these broader discussions around what's out there for us, right?
yeah, absolutely. And yeah, as we're getting close to time, I came into this and I immediately kind of had a misconception about solar industry of thinking that it plateaued. What are some other things that investors, often get wrong about this industry that, you think they should better understand, most of them?
There is a tendency, it's really twofold. One is say, oh, China won, right? And China will always win. And that could be applied to any industry, right? Any industry. The automotive industry had its response. That's why you don't see BYD cars here in the United States. And having ridden in a number of BYD cars, I can tell you they're fantastic. So that's a real threat, right? That applies to any industry, not just solar. So let's just acknowledge that this is an industrial policy question that China aggressively addressed over the last 3 decades. They decided to become an industrialized nation and put everything they could into that. All right, so that applies anywhere. So let's not talk about PV in China necessarily, because this next wave of PV is both supported from a regulatory standpoint in the United States, regardless of administration. I want to highlight this is not, I'd say President Trump is not anti-solar. So we haven't seen that. We've seen some challenges in, let's say, the interconnection queue and whatnot, but I think that's largely being sorted out in the courts. So in both administrations, back to back, I would say we see a pro PV climate, and it's a pro American PV climate. So that's important for people to really understand, as well as we're seeing similar behavior in other places. Regionalization of manufacturing is what is going to happen. I think countries have realized that they lost something important when they decided to treat China as a workshop. And so they needed to really look at real reindustrialization. And that's an important strategic dimension for any country. Um, the founder of Swatch said once that you don't have a real economy unless you make things. And I think that's something that's important for people to realize that things are shifting that direction. And I think the other piece that I would love for investors to know is that innovation is not done in photovoltaics. We're proof of that. Our company is proof of that. We're working with great companies today. Our partners in Puerto Rico is a very important example of taking great technology to start with, a great strong baseline of manufacturing prowess, making traditional PV and changing that into the most advanced photovoltaics in the world. And so innovation is not over, and it won't be over. And it's a question now of how do you protect yourselves from losing it again? And a lot of it will come down to having the right regulatory framework, and a lot of it's going to come down to innovation, and a lot of it's going to come down to sound technical choices to ensure that we can be more cost effective than you can be in China. And I think that's the journey we've been on, and I think it's a journey that we are um, have solved and will continue to solve.
And you think solar might be more of a space industry than terrestrial industry a few years down the road?
I think that the appetite for solar is going to continue to accelerate in the US, at least until the 2060s. And so we've got a long way still. As especially as you look at electrification of Africa, it's not going to be coal-fired power plants. It's going to be PV. It's going to be PV and long duration storage. And here's an anecdote I think people should realize and think about is that when Nigeria decided to bring telecommunications infrastructure to the company, it did not go and pursue landlines. It went right to 4G because at the time that was the cutting edge technology. And so they deployed the most advanced 4G network in the world at the time. And they leapfrogged legacy technologies like landlines to go to a wireless telecommunications infrastructure. We're going to see the same thing as we look to electrify parts of Africa that don't have electricity today, parts of Asia that don't have electricity today, which is less and less so because now community solar will be a thing. People will be able to go to their local provider and literally print out their solar array that they need for their home. So this is the future that we're talking about unlocking, and this is why I don't think we're going to see solar run out of steam anytime in the future in terrestrial applications. And I think that a bonus to this is going to be space-based applications. And this is going to, again, help accelerate things that we'll do terrestrially. And we've seen this happen time and time again where technology that were developed for space have made their way back down through the gravity well back to Earth. And we've been a lucky recipient of that. So there will be, I think, a co-innovation cycle that's going to happen in brown PV that is going to address both dimensions, and both will benefit from it.
Wow, incredible. All right, I'm very excited for the future of solar. Scott, I want to thank you so much for taking the time to join us today. This has been an amazing conversation, and I'm very excited for the future of solar and Caelux.
Thank you very much for having me today, and I really appreciate it.
Absolutely. Thanks so much. Take care.
Bye.